Okay, I've got one more example I want us to work through dealing with resonance in tubes, and it's very similar to one of the lab activities that you have. You may have already done, I'm not sure, but it involves a resonance tube that you can adjust the length of by filling it with water. So we can increase the level of water in this tube, and that effectively changes the length of the tube. So if you have a tuning fork here held at this end, let's say that tuning fork is 500 hertz, so the frequency here will be 500 hertz. Then as you gradually increase the level of the water, decreasing the length of the tube, eventually the length of the tube will match up with those lengths that correspond to the harmonic frequencies that are allowed for a closed-end tube. Remember, that's only the odd-numbered harmonics. So as you increase the length of the tube, let's say when increase the level of water, let's say when the water level reaches this point, it resonates. Which you can tell it resonates because the sound will get louder. There'll be a distinct increase in volume when the resonance occurs. So let's say that first instance of resonance occurs at 1.01 meters from the top of the tube. Okay, so you continue to increase the water level, decreasing the length of the tube until you find a second point of resonance where the water level is at 0.676 meters. Now you could continue to increase the water level and find probably other points of resonance, but all you need are two adjacent points of resonance in order to calculate the speed of sound in the tube. Okay. Remember the requirements for resonance to occur. There has to be a node at the closed end and an antinode at the open end. So let's look at the first instance. That means that there has to be a node here and there has to be an antinode here. So it would look something like this. Now we don't know exactly how many nodes and antinodes there are between the water level and the end of the tube, but we do know that there's a node here and an antinode here. There has to be, it has to be that way in order for resonance to occur. So let's say that this is the first instance of resonance that you observe, and then as you increase the water level, the next occurrence of resonance will occur when the water level is here, when the length of the tube again matches that requirement of having a node at the closed end and an antinode at the open end. So this would be the 0.676 meters that you measure. Right? Now, our goal here is to calculate the speed of sound. We've got the frequency, and we can use these measurements to determine the wavelength. If we look, the distance between these two adjacent points of resonance is 1/2 of a wavelength. That's one antinode. So that's 1/2 of a wave. So this distance is 1/2 lambda. And we can just subtract 0.676 from 1.01 to get that distance. That comes to 0.334 meters. So it's easy from here to get that the wavelength of the wave is 0.668 meters. That, with the frequency, is enough for us to find the velocity using this equation. So 500 hertz times the wavelength, 0.668 meters. That gives us a velocity of sound to be 334 meters per second. And in the lab, you'll compare that with a accepted value, which you will have calculated using the temperature of the room. If you know the temperature of the room, of the air in the room, you can use this equation, 331 plus 0.6 times the temperature, to determine what the speed of sound theoretically should be in the room. And hopefully those two values agree pretty closely when you do this in the lab.